Here we are looking at 13.2. In this 13.2, we are looking at the derivatives and integrals of these vector-defined functions. Again, like my vector has x, y, and z components. Often, r of t will be broken as in f of t I, g of t j, and h of t k. That's one way to think of it. And so if I want to take this derivative, I will just have r prime of t. And since these are three independent functions, they do not rely on each other, but they all rely on t. So this would just be f prime in the I direction, g prime in the j direction, h prime in the k direction. But even more important than that, this derivative has significant meaning in terms of motion, velocity, acceleration, direction is the biggest thing we can remind you of. As a reminder, the direction is r prime. We had some problems previously where it would have a point like 1, 2, 3, and it would have a change vector 4, 5, 6, t. And so each component, x would be 1 plus 4t, y would be 2 plus 5t, z would be 3 plus 6t, and I would say, oh, what direction is it heading? And you'd say 4, 5, 6. The reason we'd say the direction it's heading is 4, 5, 6 is because that's the derivative. If I take the derivative of the f, g, and h functions, I would get 4, 5, and 6. So if I need to know what direction it's heading, it's just that derivative. Onwards. That r prime has a special name called the tangent vector because we know it's tangent to the curve, but that tangent gives me the direction, that instantaneous direction that it's heading. But we want to normalize this, so we normalize it by turning it into a unit vector, meaning its magnitude is 1. So I take that direction, I divide it by its magnitude, and t can always be assumed to be a unit vector. It shows me instantaneous direction without magnitude, without speed. We strip the speed off of it when we divide it to get the unit vector because we know speed is the magnitude of velocity. And this would be my velocity if plane r of t is my position. Hopefully this is all coming together. Hopefully it's all making sense. We have lots of great things here to look at. First, let's go find the equation of the tangent line t0. Realize this equation is going to look like a line. It's going to come out looking like this. I'm going to have a point, and I'm going to have change. So that's what I should expect. If I have a tangent line, I would have a point, which I'm going to call r naught, and that change is going to be r prime naught. And that's going to give me that tangent line. So I go find my point. R of 0 is 1i. That is 0j. This is 2k. So that's kind of my coordinate. That's my original vector. That's my position at that moment. 0 is 102. Let's find out what direction we're heading at r prime. I would get 3t squared I. This is a little bit of a product rule when I get about this one. So I'd have negative e to the negative t minus 1 minus t e to the negative t. A little bit messy there, but I would have negative 2 minus t plus t e to the negative t. Hopefully you saw that product rule in action, just saving us a little bit of steps. And then that 2 cos 2t would turn into negative 4 sine 2t k. All right, and so now I have this. Let's evaluate it. That was r prime at t. Let's evaluate it at 0. Plugging in 0, I would get 0i. I would get negative 2 times negative 2j, and I would get 0k. All right, so now I have my point, now I have my quote-unquote slope or direction, and I put it together into that t of 0 equation. This is going to be 102, sorry, I'm spacing out for a moment here, plus 0, negative 2, 0. And I'm going to multiply this by some kind of parameter. Part of my issue is that I already used t in this equation, so it's dangerous to use t twice. So I'll just call this s. So that could be like t of s, the tangent vector at time s, or when I plug in something for s, it will give me the location along that tangent line t0. Let's go find the angle between these two things, r of 0 and t of 0. Feeling like I made a mistake somewhere, but I'm just going to trust my gut and say we're doing all right. What's the best way to find an angle between two vectors? That would be dot product. So I'm going to do r of 0 dot t of 0 divided by their magnitudes. Now, I do need to be a little bit careful. I was probably incorrect to call this line t of 0. Generally, t of 0 would be this guy. R of 0 would be this guy. I haven't quite normalized it to be a unit vector, but unit vector just affects magnitude and not direction. So the angle between these is the same as the angle between t proper. Here we go. We will get 1 times 0, 0 times 2, 0 times 0, and that's 0. I don't even really care what the denominator ends up being, which ends up being, what is it, 2 rad 5? I know that if that's equal to cosine, I know that my theta is then 90 degrees. These things are perpendicular. And it would make a little bit of sense that they are perpendicular. First and foremost, that this one is heading only in the x and z directions. This one has a change in the y direction. We could go further into it. This doesn't happen every time, but the dot product will always get us there. Sweet. On to the next problem. What is r? Negative 2 sine t cos t1. R double prime is negative 2 cos t negative sine t0. Done. Nothing complicated, nothing special, just regular stuff out there knowing this. And again, if you're thinking in terms of typical motion, this thing would be my velocity, this would be my acceleration. We'll learn that this is my tangential acceleration a little bit. I don't want to get too far into that. I don't want to get too far ahead of myself. That's like a 13.4 problem. We're on 13.2, so I'll leave it there. Again, the particle is moving along this roller coaster track. When will it hit the ground? Well, it will hit the ground. Let's picture. It's going along this coaster, and all of a sudden, at this moment, I should probably make it turn down if I want to hit the ground. At this moment, the little buggy particle goes flying off in that tangent direction. When is he going to hit the ground? In this case, for ground, I'm probably going to say that z equals 0. So I need r of t, I need that tangent direction, and then I need to follow that tangent direction until I hit z of 0, finding out when and where that will happen. So first, let's go find our direction vector. Our direction vector is going to be r prime of t. In this case, that's negative 2 sine t, cosine t. Derivative here is negative 1. I also need to find my coordinate. So I'll evaluate r of pi over 4. That's going to be 2 times cos pi over 4, sine pi over 4, pi minus pi over 4. That's my current location when the buggy flies off the track. That's going to be rad 2. That's going to be rad 2 over 2. And this is going to be 3 pi over 4. Now from that moment, which we just admitted, sits here, my buggy goes flying. And he goes flying, as we can tell, in the x, y, and z direction. But if the ground is at z equals 0, I do not care about x and y. I'm just going to focus on my z component. And for my z component, I'm at the location of... Sorry, I'm going to pause on that for a second. That direction vector, that tangent vector, I'm not going to quite call it t, is going to be that location r pi over 4 plus r prime pi over 4 times my parameter, which in this case, again, I'll plug in something like s to make sure I'm not duplicating. So I would bring down these things, sine t, what a typo. I would bring down these things, rad 2 over 2, 3 pi over 4, and then I would add this change vector, this direction vector, negative 2 sine t, which is pi over 4, cosine pi over 4, negative 1. But I'm only care about that z component because z is where the ground is. That's the axis, that's the xy plane that I'm trying to run into. So here, if I want to set z equal to 0, I'm just going to grab the z components. 3 pi over 4 plus s times negative 1. I want to know when that equals 0. Well, that thing's going to equal 0 when s equals 3 pi over 4. That makes sense. I did a little algebra here. I kind of combined some steps to make sure I save some space for this last bit because it says when and where. In this case, this is my when. 3 pi over 4 seconds after he leaves the track. And where is, again, when I plug in s. So that would be rad 2 over 2, 3 pi over 4, plus 3 pi over 4 times negative 2 sine pi over 4, cosine pi over 4, and negative 1. Now, I'm going to jump over some calculation here for a moment and just pop out the answer for the sake of space and for the sake of you can do square root of 2 plus 3 pi over 4 times negative 2 sine pi over 4. Be right back. So there we go. Now, square root 2 minus this yucky thing, rad 2 over 2 plus this yucky thing, and 0. I'm realizing that we didn't quite build that t of t function. So let's head back here for just a moment and build what a t of t function looks like. If you find some space, or maybe you hide it down here towards the bottom, I have to show you what a t of t function looks like, and I will take this example since it'll work out a little bit cleaner. I already have the derivative, and so what I would need to do is take r prime of t and divide it by the magnitude of r prime of t. The magnitude here would be negative 2 sine t squared plus cosine squared plus 1. Often you'll get these sine cosines that cancel. In this case, there is an uneven amount of sine and cosine, so it doesn't quite make a nice quotient. It actually ends up being a little bit ugly. I end up with 3 sine squared t plus 2. That's my magnitude. So if I wanted to build a true t of t, I would get this negative 2 sine t cos t 1, my r prime, and I would divide it by this magnitude, 3 sine squared t plus 2. So that means each and every component gets divided by that magnitude. Sometimes these work out nicely, sometimes they come out ugly, but that's how I build a plane t of t vector that we were discussing up here. Now, the t of t, like projection path, is what we did in this example and this example. On to the last one. Evaluate this integral. Well, just as we saw with derivatives, I'm going to take an integral of each piece. As long as it's continuous and I don't have anything to worry about, I will take the integral of each of those pieces. But I do want to talk for a moment. When I take the integral of these three functions, we have to recognize that f of t describes a function that relates x and time. And so this thing might have its own behavior. And so when I integrate f of t, I'm finding this area, and I'll output that blue area in the I direction. Now, when I integrate the g of t, the center function, again, this relates y of t to t. And now I have some kind of curve, I'll call it something like this. Well, that integral is going to take this area and output that area in the j direction. And last but not least, when I do the h of t function, you're going to see the same thing happen where this outputs in the z direction. I have some kind of curve over here. Not the nicest curve, but I would take this, and it would output that integral of h of t into the k direction. So when I integrate this, even though you might view it as a 3D function, it really is 2D functions. So I'm not quite finding a volume. I'm not quite finding traditional area. It's like I'm doing these three directional areas. I'm doing these three directional summations. So I'm still able to go acceleration to change of velocity, velocity to displacement, force to impulse, just to be clear about what the result of this integral actually means and looks like. Let's do a couple of these things. Again, this is just like classic antiderivative stuff. dt. I'm just going to pop out all three. This is going to be 2 sine t I. This is going to be negative cos t j. This is going to be t squared k. And I'm going to evaluate all of these components from 0 to 2 pi. Well, sine at 2 pi is nothing. Sine at, or not 2 pi, pi over 2, shameful. Sine at pi over 2 is 1, sine at 0 is 0, so this just becomes 2i. Cosine at this is 0, but cosine at 0 is 1, that's subtracted, plus 1j. T squared, that's pi squared over 4 minus nothing, plus pi squared over 4k. And that's the result, the three areas in the three different directions. There are some rules about taking derivatives of these things like the chain rule and scalars, dot product, cross product. We'll start using these, so don't think they're here for no reason. But we will use these especially as we get into the 13.3s and 13.4s. Look forward to seeing this come up again.